In this video, we will be having the verification of trigonometric identities. This is another part of our series on trigonometric identities and using them to solve trigonometric expressions. So, without further ado, I'll just give you an overview of what we will be solving. So, if you're wondering why there are certain numbers that don't have their problems, this is because actually the reason is complicated. I wouldn't want to solve or understand something that I couldn't. So I've took the liberty to I've taken the liberty to um, not answer them for the meantime. So even in that sense, I could still be able to answer the many other problems that we have in this lecture paper. So let's proceed. I suppose that these um, problems could already be enough for you to understand how we're supposed to verify trigonometric identities. So let's proceed for number one. For number one, by the way, this is something that you have to know in general. In every problem that you answer regarding verification of trigonometric identities, you have to know that you could solve on either side. You can verify either on two sides. You can choose the left or you can choose the right. However, there are limitations to that allowance because it's not all the time that um, the for example, you choose the left side, it doesn't mean that you can always have it to verify with the other side. Sometimes you just have to choose what could be simplified. So it might be quite difficult to understand at the moment, but let me show. So for number one, um, I, I won't really specify how to solve this equation in two ways. Let's just try to solve it with one way. It's pretty easy in that way. Um, you don't really have to practice solving it in various different ways unless you want to. But for this video, it will only facilitate how we're supposed to solve it in one way. So let's proceed. We still have to apply the trigonometric identity formulas that we had in the video before this video. The title is basically the formulas on trigonometric identities. So I hope you watch that video first before proceeding here, because things are going to get quite complicated, especially if you do not memorize the trigonometric identities that are specified in that video. So yeah, let's proceed. Secant x. So that could be translated as cosine x. And for tangent x, that could be translated as sine x over cos x or cosine x. And just place a parenthesis there. We just copy paste our sine x. So we won't be copying any there. The objective upon solving this expression, upon simplifying it, is that we're supposed to verify if the equation is true. We have to verify if simplifying this would get the same answer as what we have on the other side of the equation. So let's proceed to applying the Pemdas rule. We have to simplify this first before this, because multiplication goes first before we do subtraction. So just copy paste cos 1 over cos x, then place a minus sign, copy it. We can exactly simplify anything there since there are no like terms, so we just multiply them. So sine raised to 2x over cos x. as you can see, there the entire expression has the same common denominator, so you can just subtract, and in that sense you could already see that. I'm sorry, give me a few seconds to see what's supposed to be done. Okay, I understand now. What we have to do is, I suppose that you still remember this, the Pythagorean identity, whereas 1 minus sine raised to 2x is basically uh, cos raised to 2x, then divided by cos x. Now, just simplify them, cancel like terms. We have cosine x. That is, I'm sorry about that. Uh, for a while. Um, yeah, the solution is correct. You just have to simplify it further. So cos x could also be, in other words, 1 over secant x. That is the final answer. Okay, let's move to number 2. By the way, you know that your answer is already correct if they match together with the other side of the equation, the one that you didn't start simplifying upon. So as you can see, they're the same. This is already proven. Let's move to number 2. Let's try choosing the right side. We'll simplify the right side and see if it could reach this kind of expression exactly in this pattern, in this formation. So for cosecant, that could be translated as 1 over sine x plus cos x over sine x. So now it's basically 1 plus cos x over sine x. So yeah, basically that's it. This is already our final answer because it exactly equates with this one. So they're equal. Therefore, it's verified already. Let's move to number 3. So it's the solution for number 3 is going to be quite difficult. It's quite lengthy. Well, yes, there is a difference between the problem being difficult and the problem being lengthy. They could be put together. They could be both difficult and lengthy. But yeah, let's just focus on it. For number 3, we just have to simplify what we have in the numerator and the denominator. For the numerator, we have secant theta, which is 1 over cos theta times sine theta. At our denominator, we could use turn tan theta into sine theta over cos theta, and our cotangent will be cos theta over sine theta. So they basically cancel each other out, as you can see there. So we don't have to turn the complex fraction into we don't have to simplify it anymore because it's quite understood that the denominator is 1. So any number, again, that has a denominator of 1, or any fraction with a denominator of 1 will always be equal to its numerator value. So always remember that. It's very integral, especially when verifying trigonometric identities. Okay, let's proceed. 1 over cos theta, so we just simplify that, we get sine theta over cos theta. Okay, give me a few seconds to see if there are any possible mistakes. Okay, I've seen my mistake already. I'm sorry. I'm so sorry. There is an additional sign there, so put an add sign there, and it actually changes everything. We're not supposed to cancel the terms out. So the denominator is not 1. That's interesting. So just place divide sign there. make a horizontal line here. So sine theta times cos theta. As for this part, cancel out cos theta, then we get sine raised to 2 theta. At the other side, we get cos raised to 2 theta. Now, so we just copy what we have at the left side and we reciprocate. And here you can see that this is also part of one of our Pythagorean identities. This big chunk is equal to 1, basically. Now, we can cancel the like terms, cos theta. Now, we have sine raised to 2 theta. Is it equal to the other side? Yes, it is. They are equal. Therefore, this trigonometric identity is verified. It's true. Let's move on to number 4. Okay, I won't be dictating the problem anymore. Let's just proceed to solving it. So as you can see, of course, we'll be solving the left side. Let's see if it will altogether equate to 1. It looks magic, but let's go for the logic. Let's solve it and see how it became 1. It will have become 1. So okay, before we even find the common denominator in the left side, I think it's necessary to morph or transform the values that are not sine or cosine into sine and cosine. This is what I previously said in the previous video. So yeah, secant theta is 1 over cos theta. And for cos theta, we just place it as is. Then place the subtraction sign. For tangent, we have sine theta over cos theta divided by cos theta over sine theta. Alright, let's disregard the complex fraction. Let's simplify it already so that we could remove it. So 1 over cos theta times cos theta over 1, which is basically also 1 over cos theta. Just remember that we reciprocated. I did some mental math, so I hope you can cope, you can follow. Okay, so sine theta over cos theta, then reciprocate. From the other side, we get sine theta over cos theta. So you can see there that there's quite a pattern. It's basically duplicated. Both are the same. I suppose that you know what I mean already. It's pretty obvious from what you can see. So let's simplify, multiply them. So this is what we get. Right now, you can turn 1 over cos raised to 2 theta into secant raised to 2 theta. Then subtract. This could be tan raised to 2 theta. And in that case, there is a specific trigonometric identity stated in the previous video. I hope you have also taken note of it. This one is equivalent to 1. Secant raised to 2 theta minus tan raised to 2 theta is equal to 1. So yeah, they are verified. Let's move to number 5. Let's just erase this. Okay, for number 5, we'll be simplifying the left side. Let's see if we could make it equal to what we have in the right side. So cos raised to 2y minus sine raised to 2y is, this one could be equal to 1 minus sine raised to 2y. Remember the Pythagorean identity. one of the identities in the Pythagorean identity. It's pretty redundant, but yeah, I suppose you can understand it already. Minus sine raised to 2y. Right now, you could say that if you compile these two, you can get negative 2 sine raised to 2y, which is literally equivalent to what we have at the other side. So as you can see, this is what we have. Alright, let's move to number 6. Cosecant raised to 2 theta plus tan raised to 2 theta. Now, by the way, I've forgotten. I'm not going to dictate the problem anymore. Let's proceed to the solution immediately. Cosecant raised to 2 theta could be translated as 1 over sine raised to 2 theta. For tangent, of course, as usual, sine at the top, cosine at the bottom. And if there is a squared, we put squared on the numerator and the denominator values. Place minus 1. So in that sense, we could cancel like terms, and we get 1 over cos raised to 2 theta minus 1. So, I hope that nothing else is wrong so far. Common denominator, we have to find that. So this is what we get. And in that sense, 1 minus cos raised to 2 theta, based on the Pythagorean identity, it is equal to sine raised to 2 theta. Then we just copy the denominator. Right now, this could be translated as tan raised to 2 theta, because sine is at the numerator and cos is at the denominator. So yeah, this is it. Let's see if it's verified. Yes, it is verified. They're both equal to each other. Let's move to number 7. Okay, so for number 7, let's start with the numerator. Let's translate it into cosine. So this is what we get. For the denominator, secant raised to 2 theta minus 1. By the way, you might be deceived, but this one is not equal to cos raised to 2 theta. It's the other way around. One should be positive and second should be negative. Okay? So please take note of that. Okay, so below, we will have to do it the hard way. So translate it as 1 over cos raised to 2 theta and minus 1. We have to find the common denominator, so we might as well want to turn it into this. So break down the complex fraction, we get this one. So this is already reciprocated. 1 minus cos raised to 2 theta. You have to cancel the like terms because we have, and this one is basically equal to sine raised to 2 theta. And in that sense, you could still turn this into a more simplified version, which is basically cosecant raised to 2 theta. Let's see if it's equal to the expression at the right. Well, yes, it is equal. You might still be asking how I was able to find something that just basically came out of the blue. I'm basing my solutions on the trigonometric identities formula. I hope you have your index card with you. I'm being very repetitive on this because if you don't have that, I don't think there is any purpose on doing or on coping with what I'm doing right now. You need to have your own index card, and with the trigonometric identities formula listed there, at least the reciprocal, quotient, and the Pythagorean. As for the even or odd and the cofunction, that's a different story. We'll be tackling that next time, hopefully. Alright, let's proceed to number 8. We will be simplifying the right side let's see if it could be equal to the left side. So tan raised to 2x minus sine raised to 2x. Find the common denominator. But before that, we have to turn them into sine and cosine. With the sines and cosines, those that already have sines and cosines, we'll just copy paste them. So for tan, we still have to change that, so this is what we get. And for sine, we just copy paste because it's already sine itself. Now, we have to find the common denominator. So cos sine raised to 2x, just copy what we have in here. And for the other side, sine raised to 2x times cos raised to 2x. Let's put parentheses for this for distinction. Now, let's just make it quite organized. Okay. What we could do now is basically we could actually simplify. I mean, do the opposite of simplification. We can factor sine raised to 2x, and this will be 1 minus cos sine raised to 2x, and the denominator is cos raised to 2x. Now, let's try to see that, we have to see that this one is equal to sine raised to 2x, and multiplying it with this makes it, hang on, I don't think we're supposed to simplify them together, to join them together. Maybe let's write them as is, this way for now. So we could turn this into tangent, tan raised to 2x, then we multiply it to sine raised to 2x, hence our final answer, I suppose. Let's see if it's equal to the left side. So yes, they are equal to the left side. But of course, there's so many green circles. That's distinct our final answer with a brown annotation, the brown box. I'm sorry. Let's proceed to number 9. Okay. The solution for number 9 is quite lengthy, so please pay attention once again. We will have to expand the expression. So, by the way, this is what I've been talking about. It's not all the time that you can solve or verify trigonometric identities using both sides. In this case, for number 9, you can't really use or simplify the right side any further. Therefore, you are left with no choice but to simplify the left side and see what you could get or how it's going to land as 2. If it's not 2, then what's the purpose of having the equal sign in between of the expressions? So yeah, it's basically it. Let's duplicate. It's quite faster when solving math with using digital notebook, but it still has its disadvantages. So yeah, I think it makes us even. Anyways, we've already written the expanded form. Now we just have to apply FOIL method. Okay, for sine theta, we multiply them together, we get sine raised to 2 theta. Then sorry, give me a few seconds to see. There's an ant right now beside me. Okay, let's proceed. Cos and sine, we get 2, then sine theta times cos theta. Then cos raised to 2 theta. At the other side, at this part, we get sine raised to 2 theta, then minus 2 sine theta times cos theta, then plus cos theta raised to 2. Okay, so I hope that makes sense. Let's try to use a variety of colors again. So for sine raised to 2 theta, we have two of them. For sine theta cos theta, we have two pairs. We have a single pair. And for our orange color, we have cos raised to 2 theta and cos raised to 2 theta. So now let's combine them together. So we get 2 sine raised to 2 theta, and we add, so cos raised to 2 theta, and this is our final answer. Actually, no, sorry about that. We still have to factor using 2. So we draw 2 from the two expressions, from the two terms, and we get something like this. And as stated in the Pythagorean identity formulas, sine raised to 2 theta plus cos raised to 2 theta is 1. So basically 2 times 1 is 2. That is our final answer. How do we know that it's our final answer? It's proven. So it's quite verified already. So we'll skip number 10. For number 11, okay, let's continue for number 11. The solution is quite lengthy, but not that difficult. Actually, no, it's the other way around. It's quite difficult, but it's not lengthy. So tan theta could be translated as 1 over cotangent theta minus 1. Of course, we'll be finding the common denominator later. But for now, we'll be morphing the terms that are not sine and cosine. So yeah, it's pretty self-explanatory. We are using the left side to see if it could be equal to this. Hence, it would be verified in that sense. So cotangent theta 1 minus cotangent theta, then divided by, find the common denominator as well, so 1 plus cotangent theta. So now we have to reciprocate, to disregard the division sign and replace it with the multiplication sign, something that we actually have to do. So we arrive with a solution like this and cancel like terms. We get something like this. The add sign is at the denominator and subtract sign is at the numerator. Oops. Let's see, let's verify. I'm sorry, I need a few seconds. There's another ant walking around. Alright, let's go to, sorry, I just got distracted right now, but yeah, I'm still good to go. So 1 minus cot theta over 1 plus cot theta, they're verified already. For number 12, we'll skip. For number 13, skip as well. 14, skip as well. Don't worry, at least we're able to answer other problems that are quite lengthy and complicated. It's just those problems are beyond my ability to solve. So yeah. For number 15, the solution is quite lengthy. Let's see how hard it is. But that's not our objective in solving math. We should see. Let me cut to the chase. Let's just solve it. Tan theta, we have sine theta over cos theta. Then put it under secant, so secant becomes for a while. Let me write this a different way. So we have a horizontal line. We immediately join them together using the common denominator. So tan theta times cosecant theta plus cotangent theta times secant theta. So we'll solve it this way. For tangent, we have sine theta over cos theta times cosecant, which is 1 over sine theta. At the other side, we have cotangent, which is equivalent to cos theta over sine theta times secant theta, which is equivalent to 1 over cos theta. Then place an equal sign. Don't forget the denominator part. For secant, we just copy paste 1 over cos theta. Then cosecant is 1 over sine theta. Okay, so let's proceed. We can cancel the like terms already and rewrite what we have left. So we have 1 over cos theta, then plus 1 over sine theta, all together divided by 1 over cos theta sine theta. Now let's find the common denominator in the numerator. So we get sine theta plus cos theta. Okay, let's reciprocate already. So this is what we get at the other side. Right now we can cancel the like terms and we will be having this one left. Let's see. I suppose this is already final. Let's verify. So yeah, they are verified. It's true. Let's solve number 16. I think this is our last question. Yeah, it is our last question. Let's solve to end this video now. I mean, as early as possible. For sine y, we just copy it since it's already sine. Then for tangent, we turn that into sine cosine. Oops. Hang on. Okay, never mind. I just thought of something that might be confusing. It's not really confusing. So let's proceed. For our denominator, it's 1 plus 1 over cos sine y. So we keep things this way and find the common denominator in the upper part. We get cosine y and we get sine y cos y plus sine y. We could factor that. Let me spell it already. At this part, we need to find the common denominator, so we get cos y then plus 1. So let's simplify the complex fraction. Let's make our life easier. That's an ugly s. Okay. Anyways, sine y, then we factor it out. This is what we get. All together, all the more we have cos y below it, and reciprocate, we get something like this. So right now there are two like terms that we could cancel, this one and this one. Now we are left with sine y. Let's see if it's verified already. So yeah, it is verified. They're the same. That is how you solve trigonometric that's how you verify trigonometric identities. let's double check our answers. For number 1 over secant x, correct. 1 plus cosine. Actually, it's quite pointless to check verification of trigonometric identities, um, since I suppose it's already a correct answer if your final answer is equal to what we have in the other side of the equation. So technically everything here is correct as long as they're equal to one another. So yeah, that's it for this video. I hope you've learned something. I hope this video helps um, in your math endeavors. So yeah, thank you for watching this video.